Good morning, everyone. Welcome to EDP and Applied Mathematical Seminar. It is a pleasure for me to open 102 of this seminar. Today we have two excellent speakers, Sylvain Ervedoza and Emmanuel Frenot. Introducing Sylvain Ervedoza, we have the Professor Diego Souza. Thank you, Diego. You can start.
Okay, thank you, Juan. For me, it's a great pleasure to introduce Sylvain Ervedoza. He is directeur de recherche at Université de Bordeaux. He was previously in Toulouse, where I had the pleasure to visit him. And he is an expert on controllability and on PDEs. And today he's going to talk about on the reachable set of perturbed heat equation. So Sylvain, thank you very much for accepting our invitation to deliver a talk. So you have the word.
Well, thank you very much for the invitation. So today I will present a work which has now 2 years. But, well, I believe that this is an important question and that probably it deserves some additional work from the community. And so we are only at the early stage of understanding what is the reachable set of, let's say, parabolic equations and systems. So I will present a joint work with Kevin Lebache, who is now working in Paris, in RIA, and who was at that time a postdoc at the Institut de Mathématiques de Bordeaux, and Marius Tuxnack, who is also a colleague at University of Bordeaux. So if you do not know what is a reachable set and what I mean by perturbed heat equation, in principle, I will try to explain it, and I hope it will be clear soon. If it is not, of course, feel free to interrupt and to ask questions. I will gladly answer or try to answer at least. Okay. So I will start with a very rough description of what could be a definition of control theory. Well, for me, control theory is to try to describe what are the possible actions that you can do on a solution of a dynamical system. And so, I mean, of course, when you start analyzing this, you start with linear systems. So the typical example is y prime equal to ay plus bu. So this one is a linear system, and of course you have to give some kind of mathematical setting for this equation to be well posed. So in general, you assume that A is a linear operator which generates a C0 semigroup on some Hilbert space, and B will be the control operator. So I don't know if you see my mouse. Well, so B is the control operator, so which is the one which will describe how you can act on the system, and U is the control, which is usually chosen as in L2 0TU, where U is some Hilbert space. So basically here you have all the assumptions which allow you to give a meaning to the solution of y prime equal to ay plus bu. Right, so in this equation, U is your action on the system, and B will describe how you can act on the system. Okay, so this is really well, the toy model in control theory in PDE, right? And you already have a lot of difficulties when addressing control issues for this type of equations. Okay. So my objective today will be to try to describe the reachable set. And the reachable set is the set of all data that you can achieve at some time t, starting from an initial condition y naught. So in principle, the reachable set is something which depends on the time horizon capital T, okay, which is here again. So I don't know if you see it, but it may depend on capital T and on the choice of the initial datum. Okay, so basically you want to make explicit what are all the states that you can achieve when you choose your control functions U in, let's say, L20TU. Okay. So let me start with something that you may have already seen. So which is the Kalman condition, which is the finite dimensional case. Okay, so in finite dimension, you may assume that your Hilbert space is Rn or Cn, it's more or less the same, that A is a n by n matrix. Okay, and then what is clear is that, in fact, your reachable set, you do the linearity of the system, is a nothing set. Okay, so you have exponential Ta y naught, which is the part coming from the initial datum, and you have some vector space, which is given by the second part of, well, by your control function, right, by Bu. Okay, and so you want to describe what are the states that you can reach starting from 0. Well, this is clearly a vector space, and Kalman condition, in fact, tells you that it is exactly the range of the big matrix where you put B, AB, A square B all together. Okay, so if this forms a big matrix and you look at the range of this matrix, so this part here is a vector space, and this is the one which really describes your reachable set. Okay, so in particular, this, if you denote it by capital R, like this, you have basically two options in finite dimension. Either R equals to the whole space, so in this case, Rn. And in that case, your system is exactly controllable in any positive time, and it is also controllable for any perturbation, A tilde, B tilde, which are close enough to AB, right? This you can see because the range, if the range of this matrix is Rn, you can perturb a little bit by continuity. The range of the matrix obtained by perturbing A and B will be the same. Okay. If R, so if this reachable set is not the whole space, then when you look at the theorem above, it says that still you can restrict your operator A to this reachable space. So of course, this is a linear space. This reachable space is a stable by A. Okay. And you have, in fact, a system Z prime equal AZ plus BV, which is exactly controllable on R. So you see, even in that case, in fact, you start from a system which is not controllable, okay, in the sense that there are some directions that you cannot reach. But then by restriction on this set of reachable space, you have an exact controllability result. And so then you can say, yes, but if it is so, maybe then I can combine with the first point to say that, okay, if I perturb A and B with perturbations which are compatible with this space capital R, then everything should work and I should still have controllability in that space. Okay, so this is more or less what we are trying to develop in the context of the heat equation. Okay. So the problem with the heat equation is, okay, the first one is that you are in an infinite dimensional settings, which means that you have a lot of vector space which are not closed, and you do not have something as clear as Kalman type condition because you don't have Cayley-Hamilton theorem. Okay, so this is clear. So, well, even if my focus will be on the heat equation, in fact, this is a broader question which which is what happened for infinite dimensional system. So you may think, for instance, at the case of the wave equation in a ball, when you control it from a smaller ball inside. So if you do that, it is well known that you will never have exact controllability, but you will have approximate controllability. So it means that the reachable space will be dense, okay? But in fact, for the wave equation, we don't know much more than that. Okay. So the typical example I will have in mind here will be the heat equation. And just for sake of simplicity, I will consider it in 1D, okay, on an interval minus LL and control from both sides. So here I have two controls. I have one in minus L in the Dirichlet boundary condition, and the other one in plus L also in the Dirichlet boundary condition. Okay. So the general setting I will consider is the following. I have still a linear system, y prime equal to ay plus bu. Okay. I have all my standing assumptions there to express that the system is well posed. So A generates a C0 semigroup on a Hilbert space. Y is the state. B is the control operator, which express how you are able to act on your system, and U will be the set of controls. Okay, so U will be a control, small u will be a control, and it will be it will take values in L to 0t capital U, where capital U is a Hilbert space. Okay, so here for simplicity, let's assume that B is bounded. In fact, everything can be justified in a slightly more general setting, which is the setting of admissible control operator. Well, if you know what it is, it's fine. If you don't, let's assume that B is bounded and it's the same. Okay. I will add another assumption, which is very important for us, is that is the following, is that the system y prime equal to ay plus bu is null controllable in any time t positive, which means that for any initial condition, for any capital T, I can find a control U in L to 0t capital U, such that the solution of my system y prime equal ay plus bu satisfies y at time t equal to 0. Okay? So here, this is where you can see that I will really focus on the heat equation, because this kind of properties is mainly satisfied for heat type equations, okay, or parabolic equations and stuff like that. So at least for, say, heat equation with smoothness coefficients, it is well known that you have null controllability in any positive time. Okay. So in this case, the reachable set is still the same, right? So this is the set of all states y that you can achieve at time capital T when U is in L20t capital U. Okay. So the first theorem I will mention is the following. The reachable set, which, well, in principle, it depends on capital T, and it also depends on the initial condition, in fact, is independent of capital T and is independent of the initial condition, y naught. In fact, the proof is very simple. So let me just give you in these three items the main arguments. So the first argument, well, to say that y naught, well, that this set capital R does not depend on the choice of the initial condition. This is due to the null controllability. Okay, so if you are null controllable and if you are a linear system, this is really a basic algebraic manipulation to show that exponential TA y naught in fact belongs to RT0. So that's it. Okay, for T1, so then you have to prove that it does not depend on capital T. So what is clear is that if T1 is smaller than T2, the set of states that you can reach at time T2 is larger than the set of states that you can reach at time T1. Why that? Because if you can reach some state at time T1, so you take your control V on 0 T1, and you just shift it a little bit in the time interval T2 minus T1, T2, and it will reach at time T2 exactly what was at time T1, right? So this is really, let's say, a shifting argument in time on the control. So this one also is very easy, the fact that these spaces are increasing. For the last one, this is slightly more subtle. So you have null controllability. Null controllability for a linear system, we know that this means exactly controllable to trajectories. So then imagine that you are reachable at some time T2 for T2 large enough, okay, for T2 large. So it means that you have your trajectory which will reach T2, okay, at some point, will reach Y at time T2, some Y at time T2, okay? This trajectory, you shift it backward in time, okay? So this is a bit strange. So then it would be a trajectory starting at time minus T2 minus T1 from 0, and which reach at times T1 exactly your state. Okay, so this is a trajectory, and then you have exact controllability to trajectory, so you know how to reach it. It's possible. Okay, so this proves the last implication. Okay, so basically, don't be afraid. This result is based on linearity of the equation and the fact that null controllability implies exact controllability to trajectory. Okay. By the way, I think, well, I should have mentioned, but this result is proved in a work by Sedman in 86, I believe. So this is a rather old and well-known result. Okay. So then I have this Hilbert space of, well, I have this space, which is a vector space of states that I can reach starting from 0 at time t, but again, t in fact does not really matter in that business because all these spaces of t are the same. Okay. Still, on this Hilbert space, I have a family of norms. So the natural norm is the following one. So if you take z in this Hilbert space capital R, the norm of z in RT is defined as the infimum of the cost of controls which are needed to reach z at time capital T. So in other words, this is the infimum of the norm of the control u, such that when you solve y prime equal ay plus bu, starting from 0, you reach exactly z at time capital T. Okay. So it means that you have one Hilbert space and a whole family of semi-norms, of norms, in fact. Okay? So it seems a bit strange. So the first point is that you have to clarify if all these norms are equivalent or not. In fact, this is easy because, again, remember, I told you that if T1 is smaller than T2, it is obvious simply by shifting in time the control that RT2 contains RT1. Okay, so this was the first item, no, the second item here. Okay, so it means that the corresponding control is exactly the same, right? So you can compare the infimum of the controls, right? So it's easy. So in fact, this first item, you get it for free. Okay, there are no difficulty here. For the second one, For the second one, this is a consequence of the closed graph theorem, right? So all these spaces are the same. Okay, RT1 equal R, RT2 equal R, so they are all the same spaces. And you have one injection which is continuous. So this is an isomorphism. Okay, comes from an abstract functional analysis result. The problem when you do that is that, in fact, you do not really know how the constant depends on T1 and T2. But still, there exists some constant. Okay, so you see the point is that you have one vector space and you have a family of norms, RT, they are all equivalent, but okay, it's difficult to really understand how they are, what are the constants in the equivalence relation, okay? So I have to warn you that this is very important for what happens next, to fix one norm. For instance, to fix some capital T and consider one norm, the norm of R of T. And so it's important here to keep the dependence in capital T for the norm. Okay. I should tell you that at first we did a lot of mistakes due to that because we were not cautious enough on this guy. Okay. And so, in fact, the main result we have is the following. So we have, let's say, tau positive. So we fix some time. So if you wish, you can take it equal to 1. And then you consider the semigroup, which is exponential TA, restricted to R of tau. So this semigroup, we claim that first, it does not depend on the choice of tau. Well, in fact, this is clear because R of tau is independent of tau. So this one, this is for free. But we claim in particular that this forms a C0 semigroup on R tau. This is a strong statement because it means that you have all properties of C0 semigroups, especially convergence as T goes to 0 of your toward the initial data when the initial data are in R2. Okay, and also we can make explicit what is the generator, but okay, it's kind of explicit in the sense that it is more or less the restriction of A to the reachable space. Okay, so, and it gives in particular that when you consider your system, so remember at first it was y prime equal ay plus bu, and it was only null controllable. You consider this system, you restrict it on the vector space R2, and then you get an exactly controllable system in any time. Okay. In fact, this is obvious as soon as you have this, as soon as you have the second property. Okay. And so this is really the main result, because as soon as you have this, in fact, you can do all the perturbation arguments you wish. Okay, all the classical perturbation arguments you wish, the ones which are developed for the wave equation, you can use it directly and it will work. Okay. So let me give you an idea of the proof. In fact, the idea is mainly these 4 estimates, this lemma and these 4 estimates. The rest is more or less routine. Okay, so what is this lemma? It says that so there exists a constant such that for all t and z in R tau, the norm of TTZ in R tau is bounded by a constant times the norm of z in R2. So what is the difficulty here? the difficulty is close to 0, in fact. Otherwise, it would be obvious. If you are far away from 0, this is obvious because you have null controllability in any time, so there are no difficulty away from 0. What is difficult here is to prove, in fact, that this semigroup TT is uniformly bounded close to t equals 0 in the norm, in the operator norm on R2, okay, which is the statement here. Okay. And, well, in fact, this is, well, it was a kind of a surprise for us that we could prove that. But as you will see, the proof is 4 estimates. It is not very difficult. So let me try to prove it. So I take, so tau here is fixed. And so just for simplicity, I take t in 0 tau. But of course, as soon as you have this, you have semigroup properties. And so you can do any time positive, no issue. So I take t close to 0 in 0 tau. I take z in r tau. Okay? Then I want to estimate ttz in r tau. Okay, this one I don't really know how to do. So what do? I first start by saying, okay, it would be simpler if it was the norm in R2 tau, meaning the cost of achieving ttz at time 2 tau. Okay? So I will prove later that this one, in fact, this is easy to get. This part is easy to get. So I first start with that. Can I do that? Well, yes, I can do that because I know that the norm of R2 is equivalent to the norm of R2 tau. Okay, so there is a constant. I don't know the value of the constant. This is true, but there is a constant. Okay. So what's next? The norm of ttz R2 tau, I claim that this is bounded by this one, by the norm of z at time R2 tau minus t. So let's think again to what it means. So this is the norm of the control of, well, this is the norm, the control of minimal norm, sorry, such that you can reach ttz at time 2 tau. Well, if you want to reach ttz at time 2 tau, one way to do that is to reach z at time 2 tau minus t, right? So this is what is here. Okay, so this estimate, in fact, this is straightforward. So once you have that, well, you see, this is, okay, so this is the cost or the norm of the minimal control such that you can reach z at time 2 tau minus t. Well, remember, t is in 0 tau, right? So 2 tau minus t, this is larger than tau. But then if you can reach z, well, the cost of a control such that you can reach z at time 2 tau minus t, this is certainly smaller than the norm of the controls needed to reach z at time tau. Okay? So in fact, c tau here, in all these estimates, this is the one which comes from the equivalence of this norm. Okay? And then it's the same in all estimates. Okay, so as soon as you have this, well, you have, well, functional analysis comes into play, and you can play a little, and you'll get the result. Okay, so what's the interest of this result? The interest is that now you can do standard perturbation arguments. So for instance, you have something like that. So what does it mean? It means, okay, you have tau positive, then there exists epsilon small enough such that if P is small enough, so then I will come back to that, then the reachable set for the equation here, which is here, so you see this equation is perturbed by this operator P. So then the reachable space for this perturbed equation coincides with the reachable space R of tau for the unperturbed equation. Okay, so what is the condition? Well, the condition is that your perturbation is small, and it has to be small in this norm here. Okay, so as the norm, as an operator on R tau. Okay, because in fact, what you will be doing in the proof is working directly in the space R tau, right? So you need everything to be well posed in R tau, and you need everything to be quantified in these norms, right? So this is the kind of result you have. You may do something more involved with some kind of, semi-linear perturbation small enough, and so on. So this means, so here you see, we are considering, so don't read everything. So basically F is locally Lipschitz, something like that. Okay, and here what we are saying is that if you are considering something which is in the reachable space for the unperturbed equation and small enough, then you can still reach it for the semi-linear heat equation. Okay, so here you see you start from 0. This is the semi-linear heat equation, and at the end, you can still reach it at time capital T. Okay. So let me jump to the application because time is running. So I will consider the 1D heat equation. And so I don't know why, but here I change. So this is on 0 pi. And I'm controlling in the Neumann boundary conditions. So then I am really in my settings. So I have A, this is the standard Laplacian. This is defined on a Hilbert space L to 0 pi. The domain is the set of Z in H2 such that the normal trace is 0, and the control operator looks like that. Okay. And this system, this is well known that it is null controllable in any time t positive, and this is due to Fattorini and Russell using moment techniques. Okay. So in this case, we know exactly what is the reachable space. So the reachable space, this is given as follows, as the space A12 of S, where S, yes, so this is the square of diagonal 0 pi. Okay, so S, this is the square in the complex plane, right? So you were working on 0 pi. Okay, so here, what we mean by this assumption is that any element which is in R tau, this is something which admits an extension on the square, capital S. Okay, so an element of R tau, in principle, this is defined on 0 pi. We claim that it has to admit an holomorphic extension in the square of diagonal 0 pi. Okay, so the square is S. Okay, it has to be holomorphic in there. And on this square, it has to be in W12. So this one is the usual Sobolev space. Okay. So it means that the norm of F square and the norm of gradient of F square on S is bounded. Okay. And so here you see this is really exact. We have an identity. So this result is due to Hartmann and Orsoni. And it has been, the conclusion of several works, which started, so, okay, there was the work by Fattorini and Russell, and at some point, people stopped there because it was already very precise. But in fact, the description was not very complete. And then there was a renewal on this topic after the work by Martin, Rosier, and Rouchon in 2016, where they tried to characterize the reachable space in terms of the sets in which there can be extended holomorphically. And so then there have been several improvements. So with Jérémy Dardet, we did some works, but then it has been improved more and more. And this is well, the final conclusion, which has been reached by colleagues in Bordeaux, Andreas Hartmann and Marco Anton Orsoni in 2021. Okay. So then the first result, which seems to be unknown, at least to my knowledge, is that the heat equation with Neumann boundary condition, this is well posed in this space A12 of the square. So this is what is called the Bergman space, for what we know. And well, in fact, at first, we tried to prove it by hand. And we did not manage to do it. Because, I mean, okay, look at this. This is the heat equation in 1D. You know exactly what is the kernel in that case, right? So this is the Gaussian that you can, well, this is copy of the Gaussian, right? So you can compute the kernel using the methods of image by symmetry. See? So it's rather easy. Everything is explicit, but if you try to prove it by hand, well, at least we did not manage to do it. Okay. So first theorem, this is well posed. This is a well posed in A1 to S. Still, I mean, this is a bit weird, right? Because the heat equation usually generates analytic semigroup in L2 or, well, in H1 or, okay, any kind of Hilbert space in which we are used to work with. Okay, but here, be careful. This is a space of holomorphic function, and it is not true that the Laplacian is self-adjoint on this space. So in fact, if you want to prove an anicity there, well, the only thing I know is either you do it directly using the formulas, or you try to estimate the resolvent in the complex plane. But okay, is it analytic on A1 to S? I don't know. I think it is not. But I mean, this is a personal guess. Okay. And as a corollary, what we can prove is that if you consider a potential P, so P, in principle, this is defined on 0 pi, right? If you can take so if you have a potential P which admits an holomorphic expansion in the square, such that this holomorphic expansion is in W1 infinity and small enough, and the norm in W1 infinity is small enough, then the reachable space for this equation coincides with the reachable space without the potentials, meaning A12 of S. Okay? In fact, this is a bit of a surprise because in this business of reachable space, usually it seems, well, the proof seems to be very rigid and based on the explicit knowledge of the Gaussian kernels and so on and so forth. While here, of course, I mean, for P in there, for P, okay, even if it is holomorphic in the square, it can be very, very bad outside of the square, and probably you have no guess of what is the Gaussian kernel in this case. Okay. Well, you can do, well, maybe I will just jump this part just to mention that you can do some kind of semilinear approximation as well. So if you have a sufficiently nice property, you can do stuff like that. Okay. So just to conclude, we can also develop perturbative arguments based on compactness results, right? So as I told you, in fact, as soon as you have a space in which your system is well posed and in which you have exact controllability, in fact, you can do pretty much any kind of perturbative argument. Okay? So if you do that, well, if you use compactness result, basically what you need is unique continuation properties. Okay, and that's it. So this is something that you can use, for instance, to deal with non-local operators in space or in space and time and so on. And if you do that, you can recover the results in Fernandez-Cara, Liu, and Zoazua, 2016. Okay, there is an interesting question which is not so clear, and which is related to the one I just asked you about for the heat equation in 1D. In general, if you have in mind the heat equation, you are in a case in which exponential TA generates an analytic semigroup on H. Okay, on some Hilbert space. Let's say H could be L2, for instance. Okay, but then you restrict it to your reachable space, and what you get is a C0 semigroup. So do you get that it is analytic? Well, my guess is that probably no. But still, I mean, probably you get some kind of differentiability property for the semigroup or stuff like that. But this, really, I don't know how to prove such thing. But this would certainly be interesting. And this could also allow to handle more general lower order perturbations. For instance, with our approach, we are not able to handle first order perturbations. So here P is the potential. So you see this is PZ. Sorry, it's here. But if you take plus DXZ, I don't know how to proceed. Okay, and our result does not allow to do that. Sorry, okay. Also, in fact, our approach is very good when you know exactly what is the reachable space for the unperturbed equation. And in fact, there are very few cases in which you know exactly what it is. So basically, there's this work by Hartmann and Orsoni. So for the 1D heat equation with no coefficient, there is also work by Orsoni for the heat equation with a quadratic potential x squared. So here again, everything is rather explicit. You know the fundamental solution, which is given by the Meller kernel and so on and so forth. So you can really do computations which are strictly restricted to the case of minus Laplacian plus x squared. Okay. And also you have a result by Strohmeyer and Waters in the multidimensional setting, in which they consider the heat equation with constant coefficients again, no potentials, no lower order terms, and this is in the ball, the RD dimensional ball, when you control on the wall boundary. So this is a very, very restricted geometrical setting. Okay, so in fact, there are many questions on, can we try to really understand what is this reachable space for the heat equation? So the geometry could come into play. Of course, lower order terms could come into play. You may also ask a similar question for the wave equation in case you have a uniqueness condition, but no geometric control condition. Okay, so there are really a lot of questions that can be asked around this question. I'm stopping here. Thank you very much for your attention.
Thank you very much, Sylvain, for your very nice talk. So now we open the turn for comment, questions. So if anyone has some question, please just do it. Is there any question? Sylvain, I have some curiosities. The first one is your result is applicable to systems of parabolic equations for.
It is reachable for systems provided you have null controllability in any positive time. In fact, all the assumptions are there.
So you need
I mean, for system, you have several cases in which
Yeah.
you have a critical time, right?
so you cannot apply that.
When you have a critical time, you cannot apply. But when the critical time is 0, you can apply.
Okay.
Okay. Of course, the difficulty then will be that you don't really know what is this reachable space in the unperturbed case.
Okay. And I have another curiosity is
Yes.
is about the reachable space of, for instance, for the heat equation with boundary and distributed control. Are they the same?
You mean similar to this result? So there is a result, or maybe I should have mentioned it here, by Lionel Rosier and one of his students, I don't remember the name, I'm sorry, about this. But well, basically, if you control from one side, you can do some kind of symmetry argument, right? And then you go back to the case in which you have two controls. Okay? So if you know how to control from one side, at least in 1D, you see if you control at in an interval, this is more or less the same as controlling from the boundary of the interval. Okay? Because you can do some kind of cutoff arguments. Are you still here?
Yeah.
So you can do some cutoff argument close to the boundary of your control set. And then you realize that controlling from a distributed set, this is more or less exactly the same as controlling from the boundary of the distributed set.
Okay. And just can you say some words about the difficulty to treat the case where you have first order terms?
Well, I think the difficulty comes here. Sorry. Comes here. So the semigroup here, y prime equal ay, this is a well-posed semigroup on R2. So it means that it is a C0 semigroup on R2. But it has no regularizing property, right? So for instance, you do not have maximal regularity results. Okay? So you have no regularization property. So it means that this operator here, well, whatever it is, it has to take something which is in R2 and maps it to something which is in R2.
Okay.
You cannot have some loss. Okay? So for instance, if you have dxy, imagine you have dxy, of course it will not maps L2 into L2. It will maps L2 into H minus 1. And then because this is the heat equation, probably you'll have some smoothness effects, which means that your solution will still be in L2, L2, right?
Yeah.
And so this you don't have here. This is what you lose. This is the difference between analytic semigroup and C0 semigroup.
Okay. Okay. Thank you.
So, yes.
Okay, so is there any other question or comment?
Yeah, hello.
Yeah, please.
Okay. Sylvain, thank you very much for this talk. you have said at the beginning that B could be unbounded. Yeah,
Yes, absolutely.
that means an admissible operator in respect to X. When you restrict the semigroup on this R tau, B could be still admissible in this subspace.
B stays admissible in that subspace. Yes.
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 Thank you. Yes. Okay. Second question is, you can take unbounded perturbation P. It means boundary perturbation also.
No. I mean, this is the same answer as the one I just did. But
Okay.
basically, we have, since this is only a C0 semigroup, we are really restricted to the case of perturbations that we can handle.
But
Okay.
if I remember, we have showed an old result about unbounded perturbation. If P is in some small extrapolation space, for example, some Favart space of A minus 1, this results of exact, if we have exact controllability, then also the perturbed semigroup is also exact controllable. I mean, if we have an old result, I mean, we showed many years ago.
For the heat
I don't know if it's
equation,
still
or
is.
in an abstract setting, or for the heat type
Yes,
equation?
in abstract setting, yeah. If we have, yes.
Okay, maybe. Well, I don't know this result, so if you can send it to me, I would gladly look on it. Thank you.
Okay. Thank you, Sylvain.
Okay. So thank you very much, Sylvain, for your very nice talk. So now I pass the word to Juan to explain the.
Thank you, Diego. Thank you a lot, Professor Sylvain Ervedoza, for your brilliant talk.